Okay. Can you hear me? Um, I think you mute yourself, Leon. Leon, I think you mute yourself.
Sorry.
Yep.
Yeah. Should I
Yeah,
start
yeah, no
now?
worries. Yep. Okay, today, let's get started. Today, we are honored to have Leon Kling, from FU Berlin. Leon is a PhD student, supervised by Frank Noah, working in machine learning for molecular science. And let's get started.
Yeah. Thanks a lot for having me here. Today I will talk about efficient generation of molecular Boltzmann distribution with normalizing flow. So this is something I spent my PhD working on. And I want to start with some motivation. So all of you are probably familiar with DeepMind's AlphaFold, which solves protein folding. And it predicts 3D structures from the amino acid sequence alone. Now with AlphaFold 3, also for protein complexes, and they were also recently awarded the Nobel Prize for it. However, the 3D protein structure is not everything. We might also be interested in the dynamics and interactions of systems. So, for example, if we want to understand how a potential drug binds and unbinds some target protein, we might be interested in the dynamics to compute, for example, binding affinities. And for this, we usually need these dynamics, and we can get these with molecular dynamics simulations. So molecular dynamics simulation simulate the stochastic motions of molecules with this Langevin equation here. You can see an example simulation on the right. So this equation consists here of the energy or gradient of the energy, which are the forces, some damping term, and random noise. And in practice on a computer, we simulate this by discretizing this into very small steps, usually in the order of femtosecond. So then we do a very small update, as shown below here. We have to re-evaluate this equation and then perform another update step. And the problem is that many biophysical systems take quite some time, so much longer than these tiny steps, for example, binding processes, also other things. And then performing molecular dynamic simulations for these systems might be out of reach. So the question is, can we tackle this with deep learning? And I want to focus here today on a particular application of molecular dynamics, which is the so-called sampling problem. So we are not interested in the dynamics of the systems, but we are interested in generating independent samples from the so-called equilibrium Boltzmann distribution. This distribution is shown here. So this is the probability distribution for physical systems, in our case, here molecules or many particle systems. And this is given by the potential energy U of the system. And then here on the right, I have an example distribution where I showed two different states of the same molecule. And now we can generate samples from this distribution here with molecular dynamics simulations by doing these tiny steps traversing the energy surface. However, the problems, of course, that these will be highly correlated, and especially if they're high energy barriers, these might be difficult to cross, and so this iterative process may take a long time. And so the idea is to develop machine learning methods to accelerate this sampling. There are different approaches to the sampling problem. So what I'm showing here on the x-axis is the time horizon of the method, and the y-axis the transferability of the method. So molecular dynamic simulations are usually highly transferable depending on the force field, but they perform these very small time steps. Then there are enhanced sampling methods, which usually allow for larger time steps, also coarse graining, where we collect several atoms and into beats and simulate these. So we reduce the dimensionality of the system, which usually allows for larger time steps. But what I'll be talking about today is here at the other end, so-called Boltzmann generators, which generate independent samples, so essentially an infinite time step. But the problem with Boltzmann generators was that they're not very transferable. But today I'll also talk about transferable Boltzmann generators, so TBG. Another method we worked on is what we call time warp, where from these simulations we predict large steps ahead with a machine learning model. But today I'll focus on the Boltzmann generator work. And then a perfect model might lie in the top right corner here, depending on what systems or what the task at hand is. So either generating independent samples with a highly transferable models or predicting large time steps ahead so that we can see the dynamics of the system. Okay, so now what is a Boltzmann generator? So the idea of a Boltzmann generator is to sample from this Boltzmann distribution. And Boltzmann generator does this by learning a transformation, f theta, between a simple prior distribution, usually a multivariate Gaussian distribution. So all the atom positions are randomly distributed according to Gaussians. And if we then have such a transformation, what we can do is that we transform a sample from this prior distribution via the transformation and end up at the target Boltzmann distribution, or because this is something that we try to learn, probably some approximation which is hopefully close. And then the grand thing about Boltzmann generators is that even though the distribution we're predicting might be different or slightly different from the target, we can actually reweight generator samples to the actual target distribution. And what we need for this is to have access to the target distribution locally. So we have to evaluate this energy function, which we usually have access to. So for example, in MB simulation, we also require this energy. And we also need to have access to the probability distribution, which is generated by the Boltzmann generator. And then the ratio of these two gives weight we can assign to the samples to recover the actual Boltzmann distribution. However, this is only efficient if our generator distribution is close enough to the target. And the model we are usually using for Boltzmann generators are called so-called normalizing flows. These are an invertible transformation between two probability distributions, often a simple prior distribution and more complicated distribution. And these are perfectly suited for these Boltzmann generators to transform this simple prior distribution into a Boltzmann distribution. And then, as I shown before, we can transform the samples via the transformation. And importantly, we can also evaluate the probability of generated samples under the model. And also, we can also evaluate the probability of any samples under the model. And for this, we have this change of variable equation here, where we need to have access to the inverse transformation, which we have as an invertible transformation. Then we need to be able to evaluate the prior distribution, which is usually chosen such that's easy to evaluate. And then we also need this term here, which is the determinant of the Jacobian. And normalizing flows are usually designed that this term here can be evaluated as well. And with this, this allows us to build Boltzmann generators based on normalizing flows. So how do we train these? So of course, the goal is to match the output distribution of the normalizing flow with the target distribution. There are different ways to train this. One is so-called maximum likelihood training, where we simply maximize the likelihood of samples from our target distribution, approximately from our target distribution under our flow model. And as I've shown before, with the change of variable equation, we can compute this term here. And so training might look like this, so that we are matching the generated prior distribution by back transforming samples from our target distribution that we match this Gaussian distribution. But usually we won't match it exactly, but by performing this training, we also train the other direction as is it an invertible model. And there are now many instances of normalizing flows. The one I want to talk today about are so-called continuous normalizing flows. So the idea of a continuous normalizing flow is to have a continuous interpolation between two distributions. And the idea is that they are given by the solution of this initial value problem for an ordinary differential equation, where f is our flow transformation and b the vector field. And it might be easier to understand what happens if we look at the transformation, how this is defined. And this defined like this. And here on the right-hand side, I show 5 samples that are transformed via this transformation. So this x0 where we're starting at, and then we're integrating the vector field. So the vector field is shown here as these black arrows. And you can see these change based on the position, but also over time. And then if we stop before time equals 1, we get an intermediate distribution, which we call the marginal distribution. And this is also invertible, so we can also go in the other direction by simply changing the integration direction. And importantly, we again have access to the probability of generated samples, so we can evaluate samples with this change of variable equation, where here this term is the divergence of the vector field, which is expensive to evaluate, especially because we also have to perform this integration here. And so during inference, if we want to generate samples and know the probability of the samples, we have to integrate both these equations, which is expensive but possible. However, during training with the maximum likelihood training I introduced, we also have to perform backpropagation through these, which is also possible, but quite expensive and memory demanding, which hindered the development of continuous normalizing flow quite a bit. But recently, flow matching was introduced to solve these problems. So the idea is to directly learn the vector field so that there's no need to perform the whole integration. And this is similar to diffusion models where we learn the score directly. So for this, consider this marginal distribution between times t0 and 1. The t can be randomly chosen, for example, uniformly sampled, and then we also generate a sample from this distribution, evaluate our vector field at this point, and then also the target vector field we want to match against, and simply compute the mean squared error to match these two. However, this is completely intractable because this target vector field and therefore also this marginal distribution is unknown. If we had access to this, we wouldn't need to train a machine learning model. But if we had access to such a loss, we wouldn't require to perform the integration during training and therefore could scale the method significantly. And these three works, more or less in parallel, proposed how this can be achieved. And this is with a conditional flow matching objective like this. So in contrast to before, now this marginal distribution as well as the vector field is conditional, and there are different ways to condition this. There are different parameterizations possible. One widely used, and I'll also use today, or a variation of it, is this one here. So we are conditioning on sample pairs, and the samples are drawn from the prior and target distribution independently. And then the vector field is simply given by the difference between these 2 points. And we evaluate it at this marginal distribution, which is simply a Gaussian at the interpolation point at time t. And there we also evaluate our vector field we want to learn, and then we compute this mean squared error. And all these terms here are, of course, very tractable if you have access to sample pairs. And so again, similar to the maximum likelihood training, we need to have access to samples from the target distribution. So this is tractable, and we can train continuous normalizing flows with this. And this is such an amazing result, actually. But there are still problems. We can still do better. So imagine, for example, what I show here. So we have drawn 3 sample pairs and perform the flow matching with this. And you can see these connections cross. And this will give rise to a vector field which has these curves because the integration part for the vector field, they can't cross because we have an invertible transformation. And these change in direction, these curves are not desirable, as when performing the integration, for example, with an adaptive solver, the solver will have to do very small steps during these regions. Or if we do not use an adaptive solver, we need to do small integration steps in order to not overshoot and get wrong results. So ideally, we would have a straighter integration path. And this can be achieved by not sampling pairs independently, but based on the optimal transport map. As this map between the distribution is usually intractable, what we do instead is to compute the optimal transport map batch-wise. And then you can see, for example, we reorder the pairs according to the two Wasserstein distance. So essentially, we want to minimize the distance between all pairs and reorder the samples that way. I will explain this now a little bit. So the start is the same. We sample batches independently of prior samples, target samples. Then, however, we compute all possible connections and the distances to get the cost matrix. And this we then use to solve the corresponding optimal transport problem and reorder the pairs accordingly such that the distance is minimized. And these are then used for training, and this usually results in much straighter integration path. What I now want to continue with is some of my work. So the first one is about equivariant normalizing flows. This is work together with Jonas and Frank. Yeah, so symmetries are quite important in physical systems, especially for molecules. The energy is often invariant under permutations of the same atom type, also global rotations. So for example, here, this water molecule, if we rotate it, the energy doesn't change, or if we exchange these hydrogen atoms. And this also means that the corresponding Boltzmann distribution, the probabilities there will be also invariant under the symmetry operations. And for forces, in contrast to that, these are equivariant, meaning that if we rotate the molecule, the forces are rotated in the same way. And we'll see that it might be important to respect these symmetries in our Boltzmann generators. But first, how can we construct equivariant normalizing flows? So here I'm now showing an invariant prior distribution, which is invariant under reflections across this axis here. So when we have a point here and reflect it down here, the probability of this point doesn't change. So this distribution is invariant. This is just because this is easier to show for reflections, but of course, usually we are more interested in rotations and permutations. So we have this invariant prior distribution, and now if we combine this with an equivariant flow, which is equivariant with respect to the same symmetry group, then the output distribution will have the same symmetries. And this is quite a powerful result, because with that we can control the symmetries of the output distribution and match the symmetries of the output distribution to the system we are interested in. So if we know the system is rotation permutation invariant, we can construct a flow and therefore also a Boltzmann generator that has the same symmetries. So, for example, consider this sample here. If we transform it with the flow, we end up here. And this is the same as if we would have reflected the sample first, transformed it with the same flow, and then reflected it back. So the probabilities of these samples here are exactly the same, and the output distribution is invariant. And we can construct equivalent normalizing flows based on continuous normalizing flows. For that, we simply need an equivalent vector field. So as shown here on the right, where x are the current positions and v is the vector field acting on these. If we rotate these positions, then the vector field will be rotated accordingly. And this will give rise to an equivalent flow transformation. And this then, as I mentioned, can be used to construct equivalent Boltzmann generator where we have control over the symmetries of the output distribution. And for the equivalent vector field, we use equivalent graph neural networks. There are, of course, many other equivalent choices one could have used. We use this because it fulfills the desired equivalences we are often interested in, which are permutations and global rotations. But crucially, it's also quite fast to evaluate, which is important because during inference for these continuous normalizing flows, we need to evaluate the vector field quite often. And in our experiments, these equivalent graph neural networks were expressive enough. And of course, because they're graph neural networks, they are transferable. I'm not showing results for this paper because in our follow-up work, we worked with bigger systems, but we still use these equivalent normalizing flow with this architecture. So this brings me to the next work, equivalent flow matching, with this joint work with Andreas and Frank. And here we investigated how we can use flow matching for equivalent normalizing flows. So of course we could simply use the normal flow matching as before, so not the optimal transport one. Then again here for this invariant prior and target distribution, we can see that pairs might cross, in this example, this reflection line. And this will then again end up with non-straight integration path. However, also with optimal transport flow matching, where we reorder these batches, there can be problems, and these arise even or can arise sometimes even for these reflections, but they will be very prevalent for rotations and especially permutations. But I'll explain it again for these reflections. So let's have a look only at one point here from the prior distribution with all 3 points in the target distribution. So with the optimal flow matching algorithm, we would compute the distances like this. However, because this prior distribution is invariant and the probability of the sample under reflection doesn't change, we could also evaluate the distances based on this sample. So what we're doing, we are not computing the distance, but we're computing the distance based on the optimal alignment between each pair under our symmetry group. So in this case, for example, these 3 here would be the distances we would then have. And if we do this also for the others and then perform the optimal transport flow matching algorithm as before, we would end up with these connections. And you can see these are already better than the ones before where we didn't consider the symmetry group. And this will then give rise to a close approximation of the optimal transport map for general symmetry groups. However, in this work, we're mostly interested in rotations and permutations. Unfortunately, the combination of these symmetry groups, it's usually intractable to find the alignment. So we use an approximation instead for this. And this is how we do it. So we first compute the optimal permutation with the Hungarian algorithm, and then align by rotation. We also test the different strategies where we changed the order, but this ended up to be the best trade-off of computational budget and how well it worked in the end, and how close it approximated the actual optimal transport map. Okay, as a quick reminder about Boltzmann generators, so this equivalent normalizing flow and also this equivalent optimal transport flow matching training is then used to train a Boltzmann generator to generate samples for systems, and then this allows to perform this reweighting in the end. And the first system I want to have a look at is a Lennard-Jones system of identical particles, in this case 13 particles, so all particles are interchangeable, many permutations possible, in fact 13 faculty. And what you see here on the left is some pair drawn from a batch which is already reordered based on optimal transport flow matching, and on the right is a pair taken from a batch which is reordered based on accurate optimal transport flow matching, where we include the symmetry and align the samples accordingly. So blue are the 13 latent particles, orange the 13 target particles, and then you can see the connection. And you can see on the left that these transport cost from the latent to the target is significantly larger than on the right. And yeah, if we look at the mean batch transport cost here on the right, you can see that indeed the transport cost is much larger, even if the batch size increases significantly. And this is because there are so many permutations possible, we would have to increase the batch size by a lot more in order to get these close to each other. However, of course, in the infinite batch size limit, these would give the same error and both have the optimal transport connection. We also tested an even larger system with 55 Lennard-Jones particles, and I'm now showing here after training, after a trained Boltzmann generator, which is then sampling. And here I show the integration part. So when we perform the integration from the prior sample with the continuous normalizing flow. And here on the left, you can see again that this integration path, that there the direction changes, while on the right, the model trained with accurate optimal transport flow matching has significantly straighter path. And again, this is because during training, these transport costs were much higher with optimal transport flow matching. But why is this useful? So if we look now at the integration path lengths, here in blue, you can see the theoretical optimal transport map. In green is very close, the accurate optimal transport flow matching that the path lengths we get for that. And then if we only do optimal transport flow matching, the orange one, you can see the path lengths are significantly larger. And this matters because, as you can see here, the integration error is significantly larger for the optimal transport flow matching compared with equivariant optimal transport flow matching. So what is shown here is the integration error for a fixed step size integration solver versus the number of integration steps. And especially here for few integration steps, the error of the optimal transport flow matching is much larger compared to the equivalent optimal transport flow matching. And this means that we can get away with performing significantly fewer integration steps and therefore having much faster inference with the model trained where we respect the symmetries of the system. And we can also evaluate this by looking at the effective samples based on the number of function evaluations. The function evaluations here are evaluations of the vector field. So for optimal transport flow matching, as shown in blue, and then for accurate optimal transport flow matching with the same solver, which is a adaptive step size solver, we are already much better. And then if we use the fixed step size solver with quite a few integration steps, and see that we increase the effectivity again. So including here the symmetries also in the training is quite important. However, if we would have done the same with a non-accurate flow model, getting good samples for this system at all is incredibly challenging because there's so many possible permutations, which cannot be solved simply by dipole augmentation. And the last work I want to discuss are transferable Boltzmann generators. So what I showed before, a Boltzmann generator trained on one system and evaluated on the same one. So this is work with Frank. And we looked here at dipeptides, so small peptides consisting on only two different amino acids. So there are only 400 possible dipeptides. We train on half of them and use the rest for testing and validation. And these are generated with a classical force field in implicit solvent. And we only created quite short training trajectories, so these are not, so this distribution didn't reach equilibrium and might be slightly biased, but because we're training on so many and the Boltzmann generator is then able to do the reweighting, this can be fine to have not equilibrium data as the training. So the goal is to model the Boltzmann distribution of these different unseen dipeptides. So we want to condition on the amino acid sequence and then have the model to generate samples for these. And we do this with a conditional transferable Boltzmann generator. So we're training one model, condition this on the amino acid sequence, and we also have to condition the prior distribution on this amino acid sequence because based on the sequence, we'll have different particles. And the conditional for the model works by conditioning the vector field, so the equivalent graph neural network, on the sequence, which includes the particle types, but also the amino acid type. And we train this continuous normalizing flow, this equivalent continuous normalizing flow I described earlier, again with flow matching. And after training, I'm now showing some results for the dipeptides in the test set. So here's one example dipeptide. And what you can see here on the right are so-called Tika projections. So these show the slowest processes and metastable states. You can think of them like PCA projections, but instead of projecting to the highest variance, we are projecting onto the axis where along that the slowest processes happen. So this means that transition between these four metastable states here are very slow. And these Tika projections can be computed from long simulation data. So these are generated from long MD simulations, from long reference MD simulations. And then we use the same projection to project samples generated with the Boltzmann generator. And you can see that these match very well. And we can also look at the Ramachandran plots of generated samples. Here the Tika plots are already showed, and these two are not reweighted, so these are just the samples generated with the Boltzmann generator. And here on the bottom left, you can see the energy distribution. So in blue is the reference MD distribution of the energy. And in orange, you can see the distribution generated with the Boltzmann generator. And you can see that these are not completely overlapping, but because we can perform this reweighting, we can actually recover the actual target energy distribution. And this is possible because these the overlap between these two is large enough. We can also have a look at free energy projection. So in this plot, projection on the phi angle of the Ramachandran plot. And again, before reweighting and after reweighting, and the same for these Tika plots projecting on the slowest Tika component. And always after reweighting, maybe not so in these high energy regions where there are not many samples, we are matching the target free energy landscape quite well. And here for a different dipeptide in the test set, we can see again works again very similarly. We are matching the distribution here very well, seen with the Tika plots. And the energies again are slightly too high, but after reweighting, we recover the energy distribution as given by the long reference MD simulation. And again, also these projections work quite well. We tested on all 100 test dipeptides, and here we show the effective sampling size, meaning how many effective samples we're generating. And most of them are around 10. However, nearly all of them are above 1%. And then here we show the correct configuration rate. This means that all the bonds are correct, that there are no clashes, for example. For most dipeptides, this works quite well. These where it doesn't work so well is usually when there's a ring, because that's easier to do something wrong that the topology doesn't work out. And here I'm showing the results again in a table where you can see here in the bottom row, that's the important one, that we get a good effective sample size for nearly all dipeptides and also correct configurations for most of them. I want to also briefly talk about future directions. So I've shown results for dipeptide. Of course, the goal is to scale to larger, more relevant systems. And this probably requires a diverse set of MD simulations for these larger systems and also larger, more expressive models. However, we could also go a slightly different route and use coarse graining instead to go for larger systems, which of course also requires MD simulations. But this reduces the dimensionality of the problem. So for example, here on the right, we only use a single beat for each amino acid in this protein. And this could allow to scale to larger systems more easily. However, this comes at the cost of not having access to an energy function. Yeah, I'll answer questions in the end, but I'll keep it in mind. So there's no energy function for these systems if we have coarse-grained them, so we cannot do the reweighting. But as I've seen before, the results had showed that even before reweighting, the results are quite good. So they might be, depending on the application, sufficient. Another thing one can try, and which works already for the smaller system, might be interesting for these, is to use more expansive force fields, because all the results I showed are for classical force fields, which are very fast to evaluate. However, if we go to more expensive ones like semi-empirical force fields, all of a sudden the energy evaluations become the bottleneck. And especially for MD simulation, this is a big bottleneck because we're doing these small iterative steps. But for the machine learning methods, especially for Boltzmann generators, there's not much of a bottleneck because we need the energy evaluations only during reweighting. And as we are generating independent samples, we require several orders of magnitude fewer energy evaluations, and therefore can have a significant speed up compared to MD there. One follow-up work I want to highlight is this one here, which is not using continuous normalizing flows, but coupling flows instead. And here we used peptides up to octapeptides and trained the model on this. And we showed there that this is indeed transferable up to octapeptides. Here's one example where you can see the energy distribution of the proposal. Then there's something similar to the reweighting I described. You can see that then the energy distribution matches the energy distribution of a reference MD simulation very well, and also that the Tika projections match very well. And I want to conclude with some takeaway. I hope I've shown that symmetries are quite important, and it's important to, or can be important to include them in the flow architectures. I also talked about equine optimal transport flow matching, which is important if one wants to have nearly straight integration path for symmetric systems. Then I talked about transferable ML methods to tackle the sampling problem. In this case, only about the transferable Boltzmann generators. And I've shown some promising result for small systems, as for example, these dipeptides or the 55 Lennard-Jones particles. And with this, I want to thank my many collaborators over the years. Thank you for listening, and I'm happy to answer questions now. Thanks a lot.
Thanks, Leon, for the great presentation for your talk.
Thank you.
Okay. Uh, please do ask questions. Maybe we could answer the first question in the chat by
Yeah,
Rishabh.
yeah. So I'll read it really quick. I was wondering if poor small timescales are main bottleneck in scaling these methods to larger proteins systems. If, are there any data sets, in your opinion, that we should be focusing on more? I've heard that MD-cap is still not good enough. Could you clarify what you mean with poor small samples? Do you mean that the extent of these simulations is not long enough for training, so that these systems are not sampled enough? Was that the question? Yeah, I see. Yeah, that's a very good questions. Scaling to such large systems, that will definitely become a problem. However, at least for the small systems we investigated, having non-equilibrium training data was often enough to train the model. And then because we are training in a transferable way on many systems, it can be enough to see the system only, or each system only in one state, and the model might still be able to transfer to unseen systems and states it might have only seen in other systems, for example. And about the sidechain movement, in contrast to larger conformational changes, I guess this depends on the problem. Usually, I mean, we really looked at very small systems, so we were usually not that focused on that sidechain movement, but more interested in having access to all the different metastable states. Because sidechain movement one could always get with some shorter MD simulations. As for big conformational changes where we have high energy barriers, it might be more difficult to cross. So I think the more important problem, at least in my opinion, would be the second to tackle these big conformational changes with these methods. For example, even for cost grinding where we don't have any side chains, and then maybe run some shorter MD simulations which can be run in parallel on the starting states proposed by the model, and then get a distribution that way, which is then not the equilibrium Boltzmann distribution, but might be close enough.
Yeah, okay. If no one has questions, I can ask.
Yeah, go ahead.
Yeah, so what's the largest system for now? For example, in the tar flow that you show that it can generate several peptides, right?
Yeah.
So in the end, what prevents the scalability nowadays? So it's, for example, if I want to train on larger systems, is the tar flow state of the art or it's a gain flow matching model?
Oh, the task force currently the state-of-the-art model. Yeah. So with the flow matching, they actually also I was a little bit involved in this. Uh, they also trained these continuous normalizing flows with a slight modification on tetrapeptides, where it performed worse than this TAF model. So I would say the TAF flow is the state of the art, and the big benefit of the TAF flow model is that it's much faster to evaluate ring inference because this coupling flow model, which is like a discrete version of the continuous normalizing flows, and are much faster to evaluate. I mean, it could be that there's a better continuous normalizing flow model out there that would work again. I think big part of the success here was to have a good data set so there are a lot of octapeptides, tetrapeptides, and dipeptides simulated for that one. And yeah, training of this on this diverse data set was enough to scale to octapeptides. However, I guess I would assume that scaling to even larger system becomes harder and harder as there are more and more possible peptide systems, and then might be harder to show the model enough different ones. But the hope, of course, would be that then showing it only a fraction of all the possible ones is enough to be able to generalize. Yeah.
Yeah, okay. So, yeah, but I think there's also a recent paper called Falcon. Basically, they do this few step generation rates paper under review at SAR. I don't know who the authors are, but
Okay. Yeah, I don't know this paper. It might be that there are already better models. Sorry. Yeah, that's very true. So, uh, as far as I know, this is currently the largest one, but this will be interesting to see. Okay, sorry, go ahead. But
yeah.
just want to mention that I don't know the work.
Also, regarding about this call screening, you mentioned there's no
Yeah.
function for reweighting, right? But in principle,
hmm
one try either like a Martini classical force field or like a machine learning call screening force field, right, for reweighting.
Yeah, this could work, but then you would have, yeah. I mean, this I think that's a good idea. Yeah, then you would have a distribution which is similar to what you should get with the Martini force field, which might even be a better approximation of real world data than whatever classical force field we're using, or might fail in other regions. But yeah, this would be possible.
Okay, okay, yeah. Yeah, I think it would be interesting to see like people working on this, right? And it's also effective way to scale up the Boltzmann generators.
Absolutely, absolutely. And this also like one big bottleneck for this continuous normalizing flow scaling that you have to integrate this change of variable equations where you have the divergence of the vector field, and this becomes more expensive and more dimensions. So if one can reduce the dimensions, I think this helps definitely. It might also be easier problem to learn potentially if one, for example, doesn't have to consider all the side chain atoms and so on.
Yeah, yeah. Yeah, and also there are a lot of work on like Boltzmann emulators. So in the end, that you don't guarantee unbiased statistics, right? And also like time-dependent generative models like time warp and also implicit transfer operator. So do you think it's possible to cooperate this reweighting procedure into these time-dependent generative models as well to ensure the generated samples are unbiased?
Yeah, I think this is more difficult. So how we did this for time warp was that we included this in the Markov chain scheme. So after each step, we either accepted or rejected the steps based on the Metropolis Hastings criterion. And that way, at least asymptotically, you should be again able to recover the true distribution. But this is only again possible for flow models or similar models where you have an exact likelihood models and compute again the probability of the generated samples. So I think for the implicit transfer operators, they're not currently do it, but maybe there's some other clever way to reweight these in the end. This could be possible.
Okay, yeah, I do have some other questions, but I just want to make sure that everyone can ask, so I can wait for a while.
Yeah, maybe I have one question is related to the TARFL. So in the tar flow, I think it is permutational equivariant, but not rotational equivariant, right?
Yeah, yeah.
Do you have any comment on like this non-rotational equivariant model? Because the model density given by the normalizing flows are now not respect to the physics, right? It is not invariant under the rotation. And
Yeah,
I think it is a big problem in force field. If you want to learn a universal model for the force field, the invariance is very important. But do you have any comment on like for this generative modeling scheme?
yeah. I mean, it's a good question. Obviously I worked a lot of these experiences, and then AlphaFold 3 came out, right? And they
Yeah,
didn't really use it at all. So it seems the data augmentation can work quite well, which is fair. But at least I think for rotations, this is also what we observed, that data augmentation often works very well. There also for our time warp model, this is also not also doesn't respect these rotations. And yeah, this because it's a continuous symmetry group, right? I think it's easier to interpolate there. While for permutations, it's much more difficult, and there are also and there's so many permutations possible. So yeah, I guess it remains to be seen if it's important to include this or not. I'll still think that if we had a model that respect these and is as expressive as the model that doesn't respect these asymmetries, it would be better. But maybe the main issue is to construct these models that are expressive and respect all the symmetries you're interested in. I think this so it might be better to just do data augmentations for some of them at least.
I see. Thank you. Yeah, go on, Will.
Yes. So in machine learning potential field and machine learning force field, people use a lot of cutoff radius. But from what I see, it seems for Boltzmann generator, people use a lot of fully connected graphs most of the time. So what's the trick here? Does it scale well with cutoff or not?
That's a good question. I think this is partly due to the fact that the systems we are looking at are not so big, so it's possible to not have any cutoff. But I think in general it should be possible to use a cutoff. A colleague of mine, Max Schebeck, he works more on crystal structures, and there he uses actual Boltzmann generator with a cutoff, and they work as well. So I think this should work as well. Yeah.
Okay, yeah. And also another question. So Boltzmann generator generally allows a biased data set for training. So but there are a lot of biased data set where, for example, you can use enhanced sampling to generate your data set. Also, you can just generate your samples within a short simulation time. So what
Mhm.
kind of biased data set is better for training?
I think so. What we saw, what's most useful for training, is that you have access to potentially all metastable states, and that you oversample rare states. So there's also another question in the chat, like rare event sampling. So maybe I show one example I have. Let me see. Second. For whoops. For alanine dipeptide, where there's, I mean, it's a very simple example, right? But here, alanine dipeptide. So there's usually, if you're familiar with the plot, the Ramachandran plot on the left, usually this negative V state is much more likely than a positive one. But what we did, that we weighted this positive V state, which is much rarer, such that the probability is the same as for the negative V state, and then trained the model on this. And of course, the model generates also the bias distribution, but with reweighting, we are able to recover the actual distribution. However, the effectiveness of this reweighting is then a little lower. And I think this might be, yeah, a good thing to do because usually if one can identify some rarer states but has access to these, oversampling these, I think definitely can help. And then reweighting the model in the end to correct for this.
Yeah, okay. What about the increasing the temperature? For example, change to 400, 500 Kelvin. Does that also work or not?
Yeah, that's actually very good suggestions. We tried this, it didn't work very well. Yeah,
Okay.
yeah. The effective sample size were always very low. Um,
But
unfortunately, even for example, also for time warp, they're training on a slightly higher temperature and then trying to sample at the lower one didn't work very well. However, I mean, there are models that are trained at different temperatures, and then it seems to work much better, or to, at least to interpolate between different temperatures.
yeah. We also work on like transferable between temperatures. So yeah. Yeah. Okay, nice. Thanks a lot. And also congrats on your defense, like several.
Thank you. Yeah, thank you. Okay,
Okay,
I think this,
if nobody have question, maybe we will call here.
yeah, the final question. Unfortunately, I won't be at NeurIPS this year. There were some visa issues, but I'll be at other conferences.
What about Europe's? Will you join Europe's?
No, not either. No, no conference this time.